This video will be on section 1.2. We are going to start finding solutions to differential equations. So a function phi of x that, when substituted for y in a differential equation, satisfies the equation for all x in some interval is an explicit solution to the equation. So for example, we're going to consider the function the second derivative of y with respect to x, or y double prime, plus 2 dy dx minus y plus x minus 6 equals 0. And we're going to examine three possible solutions. And we're going to see if any of these actually can be solutions for this differential equation. So we'll begin with phi of x equals x squared. So we have phi of x equals x squared, and we're going to substitute phi of x in for y. So that means y is equal to x squared. Well, in this equation that we're dealing with, we need to take a derivative, and then we need to take a second derivative. So y prime, or dy dx, is equal to 2x, as you see here. And when we take the derivative again, we get 2. So the first order derivative is 2 times x. The second order derivative is just 2. So that's how I'm getting this line right here. I'm substituting in this second order derivative as the first term of our equation. Then I'm adding 2 times the first order derivative. Then I'm subtracting y, which we know to be equal to x squared. Then I'm adding x, and I'm subtracting 6. And it's as simple as that to check a solution. That's how you just plug in your y value and any derivatives of that y value. And from here, we're just going to simplify. So we get a negative x squared, but our tendency is we want to deal with positive x squared when it's the leading term. So we've actually shifted everything over to the other side, or you can say we've multiplied through by -1 both sides of the equation to get a positive x squared. I have 4x plus 1x is 5x, so that becomes negative 5x. And 2 minus 6 is negative 4, which becomes positive 4. Now this factors simply into just x minus 4 and x minus 1. So we get two values, 1 and 4, that serve as solutions. The problem is our definition said it's only a solution if it solves for all x in an interval I. It wouldn't really be fair to call this an interval, it's just 2 points. So we would actually say this is not a solution. Even though we found 2 points where it's a solution, we actually need it to fit over some sort of interval. So this is no solution. Let's now try our second example, x squared plus 5x plus 10. Again, we're going to need to take two derivatives of this. So the first derivative of x squared plus 5x plus 10 with respect to x is 2x plus 5. And the derivative of 2x plus 5 with respect to x is just 2. So just as before, we're going to plug these values in to the original equation to get 2 plus 2 times the first derivative, 2x plus 5, minus y. Remember, y is equal to x squared plus 5x plus 10 plus x minus 6. To reiterate, the reason that x squared plus 5x plus 10 is the y value is because we are now measuring whether this phi right here, x squared plus 5x plus 10, is a satisfactory replacement for y. So we get to substitute it in. Now that we have this equation, we are going to simplify the best of our ability. So we have this 2 times 2x plus 5, which will become 4x plus 10. We're going to multiply this negative sign through the entire brackets to get negative x squared minus 5x minus 10. And then simplifying, a lot of this is actually going to cancel out. Plus 10 cancels out with minus 10. Plus 4x cancels out with minus 5x plus 1x. And all we're actually left with is, let's see. Yeah, the 10s are gone. There we go. Okay. So 2 minus 6 gives us -4. But again, negative x squared is the leading term isn't usually the way we like to do things. So we'll multiply through by -1. So this will become positive x squared, and the -4 will become positive 4. Now, if x squared plus 4 is equal to 0, we know that there is actually no real solution to that. Recall that if x squared plus 4 equals 0, that means x squared is equal to -4, which means x is equal to plus or minus the square root of -4, which if you want to keep going, this would be x is equal to plus or minus 2 times I, because I is the square root of -1. But this isn't a real solution. So this is definitely not a solution. Finally, we're going to look at our last possible choice of phi, which is x minus 4. So again, we're going to take phi of x equals x minus 4. We're going to plug that x minus 4 in everywhere we see y. So we need to take 2 derivatives of y with respect to x. These are actually quite simple. The derivative of x minus 4 with respect to x is just 1, and then the derivative of any constant is just 0. So this is going to greatly simplify things because our second derivative just isn't even there, it's 0. So we'll plug in our first derivative into the equation, and then we'll plug in y into the equation, and then we will cancel out like terms. So this negative x cancels out with this positive x, and we get 2 plus 4 is 6, minus 6 is 0. So 0 is clearly equal to 0. So this is a satisfactory solution. And it's true on all intervals, no matter what x is equal to. So we have actually finally found an interval where we have a solution. So phi of x equals x minus 4 is a solution on I equals -infinity to infinity. Our interval is all real numbers. Okay, so that was an explicit solution. Remember, explicit equations have the y isolated on one side. It is y equals something, usually in terms of x. An implicit solution is when you're actually not able to isolate that y. So we'll read here, a relation is said to be an implicit solution on an interval I if it defines one or more explicit solutions to the equation on I. So for example, we're going to look at something rather complicated here. We have 3x minus 4y plus 2 times e to the 2xy equals 5. Now, try as you might, we don't have the algebraic tools to isolate y on one side of this equation. So this is going to have to remain implicit. That is, it's going to have to remain the way it is. We can't isolate y to make things look simpler. So we're going to have to deal with this as is and try to find this as a solution. Now, the differential equation we're dealing with that we're trying to find a solution to is 3 plus 4e to the 2xy times y plus 4xe to the 2xy minus 4 dy dx equals 0. Quickly to rehash what we learned in the last lecture, this is clearly not linear because even though we've got our dy dx, our y, and our constant, that's all looking good, but these are not functions of x that we are multiplying by them. These are multivariable functions of both x and y. So this is not linear, but that's neither here nor there. So we're going to start trying to evaluate whether this equation right here is a possible phi of x, a possible solution to be substituted in for y to solve this equation. So we'll start with our possible solution. Now, we need to find some sort of dy dx value. In the past, it would have been very simple. Remember, if we're dealing with y equals x squared plus 4, we can just take the derivative of both sides. We get dy dx equals 2x, all very simple. With an implicit function, or implicit equation, we have this problem where y isn't isolated. But we're still just going to do the same thing. We're going to use our implicit differentiation to take the derivative of both sides with respect to x. So that's what we're doing here. And now I'm going to break this up into smaller chunks to really make clear what I'm doing. So remember, if you're taking a derivative of a sum, that becomes the sum of the derivatives. So the derivative of 3x with respect to x, well, that's just 3 times the derivative of x. Then I can subtract 4 times the derivative of y with respect to x. And I can add 2 times the derivative of e to the 2xy. The right side of the equation turns out very nice because that's just the derivative of the constant, which is always 0. So that's nice. Moving on, we'll actually evaluate these derivatives. The derivative of x is just 1, so we're just left with 3 as our first term. The derivative of y with respect to x, well, we don't actually know how to simplify that anymore, so it is dy dx. Now, the derivative of e to the 2xy, that's our first derivative. It's going to take a couple steps in this course, so if you thought you managed to get through calculus and won't need to use your fancier derivatives, you were wrong. So the derivative of e to the 2xy with respect to x, so I could just say prime, whatever. Well, the derivative of e to the power of anything is itself, so e to the 2xy. But now we have to use our chain rule. You multiply by the derivative of the inside. Well, what's the derivative of 2xy? Well, that's a product rule, because 2 times x times y is a product of 2 functions, those 2 functions being 2x and y. So the derivative of 2x, if you remember your product rule, which is the derivative of fg is equal to f prime g plus g prime f. So the derivative of 2x is just 2 times y plus the derivative of y times f. Well, f is just 2x. And the derivative of y is unknown. We can't really simplify it anymore, so it's just dy dx. So that's how we reach this term using a chain rule and a product rule. We are going to multiply this through because, again, we know what we're trying to reach if we just scroll up. We want to reach this equation right here. So anything we can do to make our equation look like that is going to be moving us in the right direction. So we'll just multiply through by 2e, 2 to the xy, these brackets. And now we actually realize that if we were to factor out our y in our dy dx terms, we've actually created exactly what we need. 3 plus 4e to the 2xy times y, which is exactly what we have here, plus 4xe to the 2xy minus 4 times dy dx, which is exactly what we have here, equals 0. So that means that this is actually a solution. You don't reach the same simplicity that you do with an explicit solution. Scrolling up, remember, we just ended with something very nice because we started with y equals. Here, we're just looking to finish with 3 plus 4e to the 2xy times y plus 4xe to the 2xy minus 4 dy dx equals 0. And we've succeeded. So this is a solution. Moving on now to initial value problems. An initial value problem for an nth order differential equation. Remember that an nth order differential equation just means that you've got some nth derivative. So a second order differential equation would have some y double prime term or some second derivative of y with respect to x. So by an initial value problem, we mean that we're actually going to be given initial conditions. We're going to be given what y is equal to. We're going to be given what the first derivative of y is equal to, all the way up to this penultimate or second last derivative with respect to with respect to x, the n-1th derivative. If we're given all those values, we're actually able to plug them in to solve for the nth order differential equation. So here's our example. We want to show that phi of x equals the square root of sine x is a solution to the second derivative of y with respect to x is equal to negative y times dy dx squared, y to the negative 2 plus a half. But we have initial conditions. We know that what y is equal to, and we know what dy dx is equal to at a given initial value. If we're looking at the definition of initial value problem, this would be the x0 term. x0 in this instance is equal to pi over 6. So we're just going to do the same as before. We're going to start with our y equals the square root of sine x, rewritten as sine x to the 1/2 to make the derivatives easier. But we're going to need to take some derivatives of this because there is a second derivative of y with respect to x. So we need to take 2 rounds of derivatives of this square root sine x, which gets a little bit complicated. It will bring you back to last semester shortly. So the derivative of sine x to the 1/2, you know that you're going to bring that 1/2 down front as a factor and then subtract 1 from the power. And then chain rule is going to ask you to multiply it by the derivative of sine x, which is cos x. So that's how we're going to reach this first derivative. And then we're actually going to simplify this, hopefully to make our next round of derivation easier. So sine x to the negative 1/2, well, you remember when you see a negative in a power, that just means 1 over. So sine x to the negative 1/2 is the same as 1 over sine x to the 1/2. We move the cos x to the numerator, and this is our final solution for dy dx. But now we need to take the derivative of this. We have here the quotient rule explained so that we can have some help getting the derivative of this first derivative to reach second order derivative. So g of x is the name of our function in the denominator, and f of x is the name of our function in the numerator. So f of x equals cos x, g of x is equal to 2 sine x to the 1/2. So first piece here is g of x, that's 2 sine x to the 1/2, times the derivative of the numerator. Well, the derivative of cos x is negative sine x, minus the numerator, which is cos x, times the derivative of the denominator. Well, the derivative of the denominator, remember, this 1/2 is going to come out front and multiply by 2. 1/2 times 2 is just 1. But the power will decrease by 1, so it goes down to sine x to the negative 1/2. But remember, chain rule dictates that we must multiply by the derivative of the inner function, which is sine x, and the derivative of sine is cos. Now the denominator is gx squared. So we take the denominator 2 sine x to the 1/2 and we square it, and we reach 4 sine x. Now, the next 2 steps aren't strictly necessary, but we would like things to be as simple as possible before we start doing any algebra with it. So we are going to combine whatever terms we can. We've got a couple of sine x terms here. They're raised to different powers, but we're multiplying them, so that's fine. When you multiply 2 different things with the same base, you just add the powers. So sine x times sine x, but one of them is raised to the 1/2, the other is raised to 1. So add together 1 and a 1/2, and you get 3 over 2. Over here, we are going to multiply this cos x and this cos x to get cos x squared. And the sine x to the negative 1/2 will remain the same. Finally, we are going to try to get rid of this denominator. So remember, when you're dividing through 2 things that have the same base, you're just going to subtract the powers. Well, 4 times sine x, that has a power of 1. So 3 over 2 minus 1 leaves us with 1 over 2. And here, negative 1 over 2 minus 1 leaves us with negative 3 over 2. So that's how we reach our ultimately most simple form of this second order derivative. Now, at this point, it would make sense if we begin to lose track of what it is we're actually trying to accomplish here. So realize that we are actually getting somewhere here. We were given phi of x is equal to the square root of sine x. We want to know if that would be a satisfactory substitution for y. So if we set y equal to sine x, will this serve as a solution to the differential equation? Second order derivative of y with respect to x is equal to negative y times dy dx squared times y to the negative 2 plus 1/2. So what we've done and why we've done it so far, this differential equation has the second order derivative of y with respect to x isolated on the left side. Well, now so do we. So that's a big step in the right direction. So our goal will be to show that our representation of the second order derivative of y with respect to x is entirely equivalent to the question's representation. So we want to show that 1/2 negative sine x to the 1/2 minus 1/4 sine x to the negative 3/2 times cos x squared. We would like to show that is equal to negative y dy dx squared y to the negative 2 plus 1/2. Well, there's going to be an important substitution here because we actually know what y is equal to. Y is equal to the square root of sine x. So our next step is to take our value for the second derivative, and we're going to try to factor out a negative y, because in the solution that we're trying to reach, there is a negative y factored out. So let's move on and see how we are going to accomplish this. So this is our representation, and I want to factor out this negative y. So in order to do that, I have to take both of these terms and divide them by negative y, which is negative square root of sine x. So 1/2 negative sine x to the 1/2 divided by negative sine x to the 1/2 is just 1/2. So that's how we're just left with this 1/2 term. There's actually a typo here I'm noticing, because this negative should not be inside the brackets. So this is actually very important, so I'll correct this right now. We might as well address this. If it was as written, this 1/2 power would apply to the negative that is inside the brackets, whereas with it properly written, the 1/2 does not affect the negative. So this is very important to realize. Moving on, if we divide our sine x to the negative 3/2 by negative sine x to the 1/2, again, we're trying to factor out that negative sine x to the 1/2. Well, remember our rule about subtracting the exponents. We're dividing by positive 1/2, so we're subtracting 1/2 from the exponent. So negative 3/2 becomes negative 4/2, which is just negative 2. So that's how we have factored out this negative sine x to the 1/2 term. And now we can substitute it for negative y, and we're beginning to move in the right direction. Now, let's just take a quick peek back up here and see what we want it to look like. We've got the negative y factored out. Now we want the inside of the brackets to look like dy dx squared times y to the negative 2 plus a half. The plus a half portion is already accounted for, which is nice. So we just want the remaining portion to look like dy dx squared times y to the negative 2. Well, let's go back and see what our expression for dy dx is. We have the dy dx is equal to cos x divided by 2 sine x to the 1/2. We'll write that down here so we don't have to do much scrolling. Dy dx is equal to cos x divided by sine x to the 1/2 times 2. So we want dy dx squared. So what do we actually get if we square that? We would get cos squared x divided by 4 sine x. So you can see we have a cos squared x, we have divided by 4, and we have a sine x. So if we factor out dy dx squared, all that remains is sine x to the negative 1. So is sine x to the negative 1 equal to y to the negative 2? Well, that's our last question. What is y equal to? Well, y is the square root of sine x, which is equal to sine x to the 1/2. So y to the negative 2 is going to be equal to 1 over y squared, which is 1 over sine x, which is sine x to the negative 1. Perfect. Now, the interval is important. The x value that we were working with was pi over 6. We can't just say that this is true for all from negative infinity to positive infinity, because we have had some sine x's sitting in denominators all throughout. Well, when sine x is equal to 0, that will cause a problem. And also when sine x is negative, that's going to cause a problem because sine x has been under a square root throughout as well. Sine x is equal to 0 at 0, pi, 2 pi, so on. But from everywhere from 0 to pi, it will remain positive, and that is where pi over 6 resides. Pi over 6 is an element of 0 to pi. So our interval of interest is 0 to pi. Now that we know about both explicit and implicit solutions, we will just refer to them both as solutions for the purposes of this course.